We're going to look at standing waves of sound, and we need a resonance cavity to actually have this happen. This is quite similar to what we did with the strings, but this time what we're going to do is we're going to take a hollow tube and we're going to allow the waves to bounce forward and backward. And when they do so, we will get a standing wave, just like we did with the wave on a string. It's a little more complex because in this particular case, we actually have two different types of nodes. So for the standing waves, we have nodes where the air molecules are not moving on average. They're always in motion, but due to the wave. And we have pressure nodes where the pressure isn't changing. So it gets a little complicated because the pressure nodes are actually the displacement antinodes. The displacement nodes are actually the pressure antinodes. So let's take a look at this. Sound waves, like any wave, will experience interference. And if we're just looking at sound waves from two different sources, we'll start here before we talk about the forward and backward going waves. If two waves are identical and travel a path distance that is different by some integer value n times lambda, both will be in phase. Now, the reason why this happens is even if one wave travels oops, let me change that. Even if one wave travels slightly further than another wave, okay? Here's a green wave. Let's say I have a blue wave that doesn't have to travel quite as far, okay? But in fact, traveled a shorter distance, but it traveled, some integer number of wavelengths different. What I'm trying to say is both will be in phase. Both will be in phase. Notice I have 3 more wavelengths over here, okay? So my distance, my path difference is 3 wavelengths more, 1 peak, 1 peak, 1 peak, okay? But yet both are still in phase. Now, if the difference between the two waves, the distance that they travel, I'm not doing such a good job drawing these, but you'll get the idea. If the difference is half a wavelength, okay, and here we can see, some integer n plus 1/2. Oops, sorry about that. You can get the plus in there. So n plus 1/2 times a wavelength. Then what's going to happen here is a peak will line up with a valley will line up with a peak. There'll be destructive interference. We can see this illustrated when we have two speakers, one speaker here, one speaker here, and they're both giving off the same harmonic waves, okay? Now, looking at different points here, let's take a look at where we have constructive interference. We have the same distance between this speaker and this speaker. The distance is identical. So at that point, both waves will constructively interfere. What's interesting is even if one travels a full wavelength different, like to this point, speaker 1 has a wavelength less than speaker 2 to travel, they'll still be in phase because essentially just adding an integer times a wavelength is going to do nothing but advance by by an equal amount of phase. All right. Looking at points where there's a half a wavelength difference, like to this point right here. Let me show a different one. Let's say to, I'm sorry, I'm looking for a black point. So, okay, to this point right here, speaker 1 has traveled, or the wave from speaker 1 has traveled 1/2 wavelength less than speaker 2. So we get destructive interference, okay? And that'll cancel the two out. So generally, when we have two sources producing the same wave, we get these patterns of constructive and destructive interference. And these lead to dead spots. We've got to be very careful of these dead spots whenever we design some type of sound system. What we see here is maximum and minimum pressure. These are all corresponding to essentially constructive interference, where the sound is going to be louder. But along these lines right here, there are these gray regions where there's going to be quite a bit of destructive interference for a particular wavelength. And that means certain frequencies are not going to be heard very well there. So if you have a sound system with only two speakers, you'll get dead spots for certain frequencies where the sound's not going to sound as good. So in a movie theater, they'll use many, many speakers. And basically for high-end stereo systems, high-end home audio systems, they'll also use multiple speakers. Plus you get reflections off of the sides of the walls to prevent these types of dead spots. Okay, let's talk about a standing wave in an air column. Now, when I have some vibrating object, like a tuning fork, okay, that's giving off different wavelengths of sound. If I send it down an air column where one end is open and the other end is closed, it will reflect off of the closed and open end, okay? That's an interesting thing. Anytime we change the medium for a sound wave, if we abruptly change it, we're going to get a reflection, okay? Even if that's just an opening to a larger space. So we actually get a wave that's going to vibrate back and forth within this air column. Now, here's where it really deviates strongly from our wave on a string. If you remember our wave on a string, we had this wave bouncing back and forth. And as long as the wavelength was equal to twice the length divided by some integer value, like this is n equals 2, we could get a standing wave. Well, unfortunately, for this open closed end geometry or closed open end geometry, it's a little bit more complicated. Now, for the closed end, think about all the air molecules up against this side, okay? Didn't want to change color. Still wants to stay yellow. Now, they're going to hit a wall, so they can't go anywhere. So actually, their movement is going to be 0. We're going to get a displacement node, no movement there, displacement node at the closed end, okay? So that's going to correspond to 0 movement. That will be a displacement node. At the open end, it's open to free atmosphere. These molecules can vibrate back and forth as much as they want. But the problem is, even though this is a displacement anti-node, okay, it actually, because it's open up to normal pressure, is a pressure node, meaning that the pressure can't change there because it's just open to open space. So this leads to some rather strange behavior. Okay. Going back to our wave on a string, remember when we had the fundamental mode, we said that the fundamental mode is twice the length of the string, that the wave would fold itself over like this, okay? That this would be the length of the string between here and here. And our fundamental mode would have a wavelength twice as large as that because this side would be folded over. Well, for the closed open end, what we actually have is 1/4. Oops, I'm drawing 1/2 and I'm telling you 1/4. 1/4 of the total wavelength. That's because we have our displacement node at the closed end. We have an anti-node at the open end. If we allowed the wave to completely fold out, we would have, again, closed end, then the open end, then at twice the length of the tube, we would get a half wavelength, and at 4 times the length of the tube, we would be able to get a full oscillation, okay? So this only represents a quarter of the total distance. That's this far right here, okay? In terms of the total standing wave. So this open-closed air column is really, really strange because it only creates a standing wave for the fundamental, which is a quarter the length of the entire tube. Okay. Now, gets even more complicated. What about the higher harmonics? How do they work? Once again, remember, we're just going to look at the displacement node, the place where the molecules can't move, okay, displacement node, and the anti-node, where there's going to be the maximum amount of movement, where the tube is open. Okay. Now again, I'm trying to see, here's the open end, this is reversing, here's the closed end. Again, we can represent this blue line can be the displacement of the molecules, okay, where the red represents where the pressure can build, okay, and the blue represents where the pressure cannot build. All right, very, very complicated. So here's our fundamental. Our wavelength is equal to 4 times the total length of the tube, or the length of the tube is 1/4 of a wavelength. Well, to get to the next one, remember, the open end has to have an anti-node and the closed end has to have a node. So I've got to go through 1/2 an oscillation to another node, and I can't stop until I get to the anti-node at the open end. So I have anti-node, node, anti-node, node, anti-node. Well, this is 3 times the frequency of the fundamental, or 1/3 the wavelength of the fundamental. What happened to 2? Well, we skipped 2, okay? In fact, as we go to the 5th one, here we go, node, anti-node, node, anti-node. Can't stop until I reach an anti-node, node, anti-node, okay? So this one becomes 5 times the frequency. So the interesting thing is, when we have a closed and open end, our first or fundamental harmonic, the wavelength is equal to 4 times the length, okay? The next harmonic, sometimes we call it the second harmonic, sometimes we're consistent with the integers and we call it the third harmonic. That wavelength is equal to 4/3 L, okay? The next harmonic, 4/5 L, okay? And then finally, 4/7 L, okay? All right. Now, what this means for a closed open-end resonator like this, the frequencies are going to be offset a little bit differently, okay? So the fundamental is going to be this far from a frequency of 0, okay? Frequency of 0 doesn't really mean very much, but let's say that my fundamental here, we'll use real numbers, that makes it easier, is 100 hertz, okay? Now the next harmonic, what we might call F2, what we might call F3, depending on what textbook we're looking at, we would say that that is equal to 3 times the frequency, or 300 hertz. Okay, the next one would be 500 hertz. See what's going on here? The next one would be 700 hertz. So our fundamental here is 100 hertz. Okay, that's where this whole pattern starts. However, the distance between these harmonics is actually 200 hertz. Okay, from 3 to 5 is 200. From 5 to 7 is 200. Okay, so very interesting, and we'll see that this has a very important effect in some woodwind instruments like the clarinet, where it's actually missing places where you would expect a harmonic. Okay, this leads to a warmer sound because some of these other harmonics are actually missing, putting more energy into the fundamental. Okay, so again, we see this in organ pipes where one end is closed, one end is open. We see this in musical instruments such as the clarinet. One end is open, one end is closed. And again, if we talk about the fundamental frequencies, okay, I should say the harmonics. The fundamental frequency is the velocity divided by 4L. Remember, for the fundamental, lambda 1 is going to be 4 times the length of the resonance tube. So that's where that 4L is coming in right here. Okay, so frequency is velocity over wavelength. All right, velocity over wavelength for the fundamental, and all the higher ones will go by this odd integer pattern. Okay, 1, 5, 7, 9, etc. There are no even multiples for the fundamental harmonic when, again, one end is closed and one end of the tube is open. We're going to actually do an experiment like this in lab. We call this the speed of sound experiment. And the speed of sound experiment, we're going to use these fixed wavelengths that we've just looked at right here. Again, 4L, 4/3 L, 4/5 L, and so forth, okay? To determine the wavelength of sound, we'll use fixed frequencies from tuning forks and then say V equals wavelength times frequency. Okay, that's not the only possibility for a resonance tube. We can have one end open, one end closed. Technically, we can actually have both ends closed, but that's a difficult geometry to generate sound from. It's not really usually used in musical instruments, so we avoid that. If both ends are open, what we are going to get is a displacement node at the very center, okay, and displacement antinodes at each end, okay? In terms of pressure, well, the pressure does just the opposite. At the open tubes, there are pressure nodes. At the center, there's a pressure antinode. So the pressure is varying the most at the center of the tube for the fundamental, and it's not varying at all at the ends. The molecules are moving the most at the ends of the tube, and they're trapped, they're squeezed at the center where they can't go anywhere. So what type of pattern is this going to set up? Well, here we go. Now I've drawn N and A for pressure as opposed to displacement this time. Again, wherever you have your pressure node, you have a displacement antinode, and vice versa. So if I were to draw what the displacement was doing, it would look something like this, okay? Okay, displacement would be greatest at the ends and least at the centers. Okay, just the opposite of what the pressure is doing. And again, displacement means how much are these molecules moving on average due to the wave. This, I got to be careful here. This, am I doing this right? Yes, I'm doing this right. That would be the next harmonic. Okay, so here you can see the combine. What is the displacement doing? And again, if this is our equilibrium for displacement, this shows how the displacement will vary at the different positions. And the red represents the fluctuation in pressure. A little bit complicated, these things. So again, you can see now with the displacement included there, and you can see where the displacement nodes are. Now, what's interesting here is if we look at this first fundamental, the lowest frequency we can make, this is 1/2 of a wavelength, right? That's 1/2 of a wavelength, because we go from antinode to antinode. So making both ends open actually makes the wavelength half the size as what it was for the closed open. Now here's the interesting part. Our second harmonic is 2 times the frequency of our first. We didn't have that with the closed open end. Okay, it makes one complete oscillation. Starts from the bottom, goes up, and then goes back down. So here, the wavelength's equal to the total length of the tube, much closer to what we saw for the wave on a string, okay? But really, it's the pressure, which is the one that's acting like the motion of the string. Okay, so in any case, when both ends are open, our first harmonic is twice the length of the tube. Second harmonic is the length of the tube. Our third harmonic is 2/3 the length of the tube. And our frequencies go by F1, twice F1, 3 times F1, where F1 is equal to the velocity divided by the wavelength, which is twice the length of the tube for the fundamental. Okay? So in an open error column at both ends, here's what our equation looks like. N can now be any integer. It's not odd, it's not even, it's any integer, okay? And again, for the fundamental, we take velocity divided by wavelength. For the fundamental, the wavelength is equal to twice the length, okay? Now, to compare and contrast, f of n for the closed open end was n v over 4L, where n was, I'm sorry, where Fn was n times F1, okay? Where again, n was restricted as 1, 3, 5, all the odd integers, okay? So open at both ends, closed and open.